Hello everyone and welcome to another episode of No Orientation Programming. I'm Joe and today we will change something in the system core. I have thought about the events and messages between the processes in the gaming process, and I think the concept is cool. But we have to change something in the pipe. So let me explain. It's not that easy. Okay. Step by step. Week 23. Okay. Pipe 3 and 1. Come on. Stop. So core pipe. Okay, so this is a very good example. This is a very good example where okay, overview, gamer states, component. Okay, events. Yeah. So example. Okay, this is Oh, okay. Damn it. I have deleted something I didn't want to delete. But the good thing is we have view mode. Yeah, that's a cool mode. That's a cool mode, matching. So I have deleted one of the, let's see, maybe I think what was the gaming overview? Maybe this is the diagram I'm looking for. Yes. Turn to live version. So this is the overview. So, and this is the event part. Close, let's see. So this is the system overview. This is gamer states entry, not connected, connected to lobby, and joined to match. And then we have the events of the gaming process. Looks like this. That's fine. Gaming events, I think it's for yep. What the hell? So yeah, that's better. Okay, so we're back in business. So as soon as we have a detailed version of the system structure like this, we have processes and the abstract version of the process, the abstract interface, and we have the inside of the abstract process gaming, consisting of the dispatching part, the lobbying part, and the matching part. We have we see how these parts are connected to each other, and we see the type of events that can be sent from one process to another. So, and as soon as we have this, we can make timing diagrams, timings, case 1. And this is such an example. Oh, the server is working, that's cool. So, as you can see, we have we have this structure, and we can display multiple cases with a sequence diagram, and one case is to, or let's try to open multiple pictures. It's easier, I think. Yeah. This one is the first, and then we have then this one. Come on. Yeah, that's perfect. So this is the structure, and that's one case, one possible case. The first case is that the user is connecting to the gaming process. Yes, so this is not a user is connecting to the gaming process. The dispatching part is relaying the connect event to the lobby, and the lobby is sending back a frame. So we have connect, frame. Then multiple times the user is sending a key event. So key, frame. Eventually, all this configuration has been completed, and then the last key, the start key, will be sent to the from the user to the lobby. So we have key. here we have 3 lifetimes: the lifetime of the lobbying process, the dispatching part, and the matching process. As we can see, the matching process is the lifetime of the matching process is shorter than the lifetime of the parent process, gaming. The lobby and the dispatching part are what I call service processes. That means the lifetime of this process is the same as the parent process, as the lifetime of the parent process. So the last key is the start key, and I don't show the user integrating process because it's not needed at this point. So this point indicates it's coming from somewhere external. From the user interacting process, we get the key to the dispatching part. And the dispatching part is sending the key to the lobby. And the lobby finishes the configuration. Should be working. Hopefully the stream should be working. Live, is this live? Yep. Yeah, wonderful. So, okay. So we get the key from an external system, and the key is the last key for the lobby to start the game. So the lobby is not sending a frame because it's just creating the create event, sending the create event to the dispatching part, back to the dispatching part, and the dispatcher of the gaming process is creating a new matching process. And as soon as the match has started, we get the frame. So in this case, we get key, create, frame. So we send a key into the system and we get back a frame. But internally, this may take multiple steps. So on this side we have the structural information of the system, and on this side we have one case of temporal behavior. So okay, so this is fine and easy, but there are some cases which are not as easy, yes, because the first thing is that if we send a key into the system, then it takes some time to get back a frame, and this time isn't defined in any way. It can take up to multiple system cycles, and that's actually a couple of milliseconds. So we just have a certain delay, and if we send a key into the system, then multiple things can happen, like creating a process and doing some stuff and calculations, and then we get back a frame. One case is very interesting. For example, the abstract view, the abstract interface may be quite easy. In fact, that the valid alphabet of the input alphabet is quite simple. we can only send a connection, a connect event, a key event, and a disconnect event. So we have three different events. So the input vector, the input set is quite simple, but the resulting internal state is quite complex, because we can send a connect, and then we can send multiple keys, then we can stop sending keys until one of the processes decides to kick us with a disconnect message. But what happens if we send exactly in this moment a disconnect by ourselves? Who knows? What should the dispatcher do in case of multiple disconnects? Then another case is, what happens if, so we send multiple keys. What happens if we have so many keys that the input queue of the matching process is full? Should we discard a message? Should we keep the message somehow? Should we block something? It's not that easy. Especially we cannot we shouldn't drop disconnect events, because then the number of players gets out of sync. So it's not that in the inside of the process it's not that easy. Another case is, what happens if a matching process is running and checking the input queue all the time. So we are processing the input queue all the time. But then at some point the match finished, and then we are stopping to process the events. And then we go some steps further, but meanwhile we go some steps further, and then we return, for example, positive in the process. So we are informing the parent process that we are finished. Maybe we send the last event finish to the dispatcher, but the time between processing the input queue and finishing the match and sending the last message in the output queue, there is a gap in between. What happens with the input queue in this case? What if we send stuff into the input queue? Then we have some unprocessed messages in the input queue, and I thought about, what should we, maybe we could flush the input queue, but again, we shouldn't flush events like a disconnect or a move. So I think the best approach is to do something else. I think it's better to somehow close the input of a pipe, so the dispatcher knows immediately, okay, the process may not be over yet, but I can't input any information now. So it's coming to an end. It's coming to an end somehow. and I can send a key event. So okay, I can, if I get a key event and I check the input queue and I can send something into the input queue, then it's fine. I think it's fine. So I think it's fine to drop the key in this case. If the input queue is full, no, not full. I don't know yet what to do if the input queue is full, but in the case the input queue is closed, I can drop the key because I know, okay, the matching, the gamer who sent the key is registered at the matching process at the moment, so I have to send the key to the matching process. But if the matching process declines the input of new keys, then I think it's okay to drop the key, because the matching process tells us, okay, the game is still at my side, I'm responsible to process the event, but the input of the keys is closed. The input of events is closed. So the dispatch, this is a special meaning. So I think in this case it's safe to just drop the key. I press a lot of keys, I see the match, then the match says, okay, we have a winner and the game is finished. And then I still keep sending keys, but the keys are not recognized anymore. The matching input is frozen somehow. So the match is just ignoring input, key input. And I think I have to drop the keys on this side. Maybe I could indicate. We could indicate the possibility of closing this point. Maybe this is a good idea. Oh no, oh, stop. Okay. A build. Build. Gaming event for PO. Okay, so maybe we could. This is the dispatcher MD. This is MD. No, DM. This is DM and pointing from the dispatcher here. So I think this should be it. Yep. So now we have a little round area here. Plant OML. Component diagram. Sequence diagram. So we have multiple end styles von error. Yeah, that's it. I've used this notation at the moment. Ja. Actually, I think it's okay. So this process is able to disconnect the input queue. I don't think it's necessary to disconnect the input queue of the lobby, because maybe it's necessary, but it is necessary. This is strange. It's more like it's not round. That's interesting. It's not round. It's something else. Component diagram. Do we have different arrows in the component diagram? Oh, it's not documented here. So okay. Good enough. I think it's good enough. So it's DM part here. Nice. DM part here. Okay, fine. So, so next step. So this is the reason why I want to be able to close a pipe. We have something similar already in the pipe, and this was implemented because of a filter structure, a signal processing structure, and yes, but it's different. So we have two sides. So example. So let's see, overview, pipe overview. I've prepared something, and this looks like this. The pipe structure. Hi Nick. Hello. So today we do fancy stuff again, because now is the time. We have reached a certain point, a certain situation, and that's the reason why I'm doing this stream, because the gaming project, the gaming server project, is a perfect example for quite a complex system. Yeah, sometimes we do fancy stuff. Sometimes, and sometimes more often. So we have a very special case at the moment, because the gaming system is actually, from the outside, it looks quite easy. If we have a system, then a system has one or multiple inputs and outputs. And between this stuff there happens the magic. The number of different things we can input into a system we call the alphabet. In this case, it looks quite easy, because it seems that we only have 3 different types of of valid symbols we can put into the system, and only 2 output symbols. So it actually looks quite easy. But on the other hand, the inside of the system is behaving in a certain way. We have a lot of different timing situations, because maybe I should do an example. Example, yep. Gaming process, and let's do something else. We have begin. Hopefully I remember it now. I think it's called aligned in LaTeX, because it makes the equations more beautiful. So let's make an example, and this is an how is this called? An linear time invariant system. Yes, LTE system. I think it's called like this. So, and then we have a head, and this head is, in the head there is an X. Oh, that's beautiful. Okay, so, and then we align this thing, and we say we have the matrix A multiplied by I have to remember this stuff. It's a long time ago. BU, and then we have new line, and then we have head. The output epsilon is equal to C head X plus D head U. Yes. So I'm not sure this is the new X. Let's see, hopefully I see this matrix, this equation somewhere. I think the diff, yeah, maybe this head indicates that this is in vector, and I think, yeah, I think the change, one moment, I have to, I have a document in which I can look up. One moment. Uy. Doc. Yes. Yeah, the script. I'm opening a script. One moment. I'm not allowed to show, I think. Come on. It must be somewhere a long time ago. So yes. Okay. So Yes, I think this is it. This is it. We can also, so this is the linearized version. The but this doesn't look beautiful. This doesn't look beautiful. So we should, yeah. So let's say, I think the head isn't cool. Does not. Yeah. We make it. We make a point. Point over x. So we can. It was correct now. It was correct, but so there are different. I think it was correct. There are different styles how you can do it. And as you proposed, I think that's the more beautiful version. So how can we make in LaTeX? LaTeX actually. Functions, supported functions, and then we have somewhere we have the head. Yes, this is the head, and we want the, as you said, the point. It's not this math ring, huh? Almost. I don't see it. I'm blind. Oh, that's interesting. Inside text. Okay, this is inside the text environment. This is not what we want. Let's. Wie kann ich in LaTeX einen Punkt über X machen? Yeah, let's try a dot. Thanks, Nick. Yep. Nice. 1 point for you. So, oh no, yeah, then we have to. So, but the general version is, so the big, the capital letters are the uppercase letters. The uppercase letters are matrices, and the lowercase are vectors. So, yep, and this is the more general version, that is some function x that could be nonlinear, f, and then we have h. So this is the more general version of it. Here we could say x0 is equal to x of time 0. Yep. Okay, I think this is it. Because these are not only vectors, but also vectors dependent on time. And that's the reason why we have a dot here. That's the first derivative of x, of the vector. Okay, why am I showing this? I don't want to be too fancy. The reason is that let's check let's check the format of this stuff. That is the format, the size of these things. So we have column vectors. That means they always have the second size 1. So we have, and the notation now, we can do any notation, but I just choose one now. That is, we say the notation is n1. So How does this look like? Oh, come on. Yes, n1. So this is not beautiful. I think this is better. So this vector has the size n and 1. Let's call it m and 1. So the matrix A, that's the so what is x? X is the state vector, the vector of the internal system state, and the matrix A must have, so the vector x has the same size. U has a different size, let's call it p and 1, and this matrix must have m and m. Yep. And this matrix must have m and p, I think. Yep. Yeah. Let's make a C dot in between. Yeah, I think this is better to see. So, because I want to show you something. And here we have n1. Yeah. And then we have here 2m1, and here we have p1 again, because this vector has the same shape, of course. And here we have the format of the matrix here is np. Yeah. So and C has the format nn. No. nm, and I think this is it. So let's check again together. We have a matrix. This is hard for you to read. Oh, come on. Yes, this looks better. Come on, make it bigger. Oh yes. So even bigger. Okay. Now, what do I want to show you? A system has inputs, and the inputs are the vector u. The size of this vector is number of p inputs. As the number of rows is the inputs, and the number of columns is 1, because every vector has the vertical size of the width of 1. So it's a column vector. We have inputs and outputs. The outputs are the vector epsilon, and the vector epsilon has number n outputs. And in between we have a number of system states, and the number of states is m. So if we multiply a vector with a matrix, then the inner number must match. So here in this case mm, and here pp and pp, and the output of this multiplication, the format is the numbers on the outside. So the format of this multiplication, the result, has the format M1, and this and for additions the format must match. So we can only add two vectors because the result of this such a multiplication is a vector of size m and 1, and we can only take the sum if the format matches. So m1 plus m1 equals m1, and then we have n1 plus n1 equals n1, and looks fancy at the moment, but the reason why I'm telling you this is this, because in this case we have defined a system in which we only have one input, and this input has a low complexity, but the number of states that can exist, the number of situations in the system state, seems to be higher. And this makes the whole thing difficult, because from the outside it looks simple, because we just can connect and we can disconnect and we can send in some keys and we should get some frames. But if we send a key, which is just one input, one event from one input, if we have a key, then we have a lot of different system states that can be that are possible. For example, how many people are in the lobby connected? Is the match still running? Or isn't it running? Did we just create the match? Are we in the process of creating a match, or are we in the process of shutting down a match? What is happening? Who is moving to which side? And this is the inner state we don't see. So we have to be careful to keep the system complexity low. So this is the reason why we should have an eye on it. Yeah. So, and as we discussed earlier, in general, we have a key input, and this key input this key input can be processed as follows. For example, we get a key and then into the system gaming, and then the dispatcher moves the key to the lobby, and then we get back a frame, and then we send out the frame. So that's the easy case. Key, frame. If we send a key, then with a certain delay we get the frame. So we make an input, and then the system is working. And then sometime later it sends out a frame. This time can be shorter or longer, depending on, maybe in this case, we send a key in. If this key is the last key to start the game in the lobby, then we send the key, then the lobby isn't creating a game, because it's creating it's sending a create event to the dispatcher. The dispatcher sees, okay, we have to create the match, and then we are creating the match and sending in the configuration, and then the match is starting and sending the frame, and then we get this frame from the match, but the user doesn't see from which inner process this frame is coming. From which process this frame is coming from. So from the outside it looks quite simple, but it's more complex on the inside. So as discussed earlier, what happens if the matching is process is created at some point, and then the matching process is running. And what does the process do? It's processing all the inputs from the input queue. This is a queue, and it's always checking the input queue and just taking the events that are placed into the queue by the dispatcher. What if no one is sending any keys? No user is sending any keys, but the matching may be the last key already set the direction for a ball, for example. The last key changes the direction of a ball, and then all the users just have to wait that the ball is rolling towards some goal, whatever. So the condition to end the match may be at this point just a matter of time. So at this point, it's just a matter of time until the match is finished. So we sent the last key, we changed the direction of the ball, and the ball is moving towards a target, and this finishes the match. So everyone is waiting, and then the match finishes. After the match is finished, it's shutting down. So we are moving in the next states, it's preparing the statistics, for example. The matching process can do final tasks like creating the statistics or calculating the statistics depending on how complex this thing is. So it has stopped processing the keys from the input queue, the events from the input queue. But what if in this shutdown sequence, what happens if multiple users send multiple events like keys and disconnects and moves? What if in exactly this moment someone from the lobby decides to step into the game, join the game, because the person thinks the game is still running, but we are in the shutdown sequence of the match, and then it tries to move into the match. So even in this case, we have because this X vector is so big, we can have multiple cases. If someone joins the match from the lobby at exactly this moment, then we are finishing the game, but the lobby from the point of view of the lobby is that someone left the lobby and is in the match now, but the match doesn't know that someone joined, and the finish statement just moves the people who were in the game before the last move, and then we lost the gamer. So this is very dangerous. We have to be very cautious. But to make it way easier, because we could theoretically if a match process is dying or finished, so it's finished and it doesn't do anything anymore, then theoretically we could in the parent process, before repelling the process, meaning deleting the process, we could check if there are unprocessed events in the input queue, and then we could, in the dispatcher, we could check the input queue of the matching process if something was left. But This is more like a hack, like a cleanup hack. And because of that, we changed the behavior of the pipe. The pipe has an overview. And I have not inserted the overview yet. The pipe looks like this. Or should look like this. This is our target. Our goal for today. Will be the pipe should look like this. We have two to-dos. Pipe overview. To-dos. Use and check move semantics. And then the second one is rename functions. Bad, but whatever. And then use success instead of bool. So at the moment, a short explanation what is happening. At the moment, the pipe has two functions. That is the commit function. The commit function. Pipe. Commit. And this commit, add an entry to the queue. So if we have an object and we commit the object to the pipe, then the object gets appended to the queue, inserted in the queue. So the commit function inserts something in the queue. Okay, and the return word is the return value is bool. And in this case, we check is the current size bigger or equal than the size max. Then return false. We were not able to commit. We weren't able to commit the value. Otherwise, if we can push something in the queue, then we return true. So this is the first function, and on the other side we have the get function, and the get function is kind of stupid, but okay. Yeah, similar. It's similar. If we don't have a size, we return false, and otherwise we return true. We were able to remove an entry. Okay. So then we have another function. So one moment. That's interesting. Because we have a function that is called bool. The pipe is divided into an abstract, into a base class. The base class defines all the stuff that is independent of the type. Because the pipe can have multiple types. In this case, it's main gaming. So in this case, our pipe is a JSON value. So we have JSON values in the in the pipe. We can have integers in the pipe. We can have structures or classes in the pipe. So it's like a vector or a queue. Actually, it is a queue, which can have just different types. Okay. And this class, depending on the pipe, is derived from the base functions. And in here, yep. So we have helper functions like is empty, is full, size max set, size. So helper functions on the one hand. On the other hand, we have, yes, a pure virtual function to push try. That's interesting. Okay. Yeah, that must be implemented by the derived class. How old is this class? This has been created in 2018, and I'm using it since 2018. So, and now we have to change something. Oh, I hope I'm still able to change something in there. Okay, so the goal is to yes, we have an end of file signal. So what is a pipe? It's a queue of particles and corresponding timestamps with up to one parent and multiple children. Yeah, the pipe actually is quite cool. I'm using it. For example, I'm using it in the TCP listening, and the TCP listener is, for example, here we have a pipe of sockets. And the pipe is a peer file descriptor socket. And if we create a listening local, for example here, we want to add a peer, then it's working like this. We execute the peer add function on the peer list update. This is the debugging process, and in the debugging process we have the function, like everywhere in the system we have the process function, and this process function is called every system cycle, so every some milliseconds, and every milliseconds we check the peer list, or we update the peer list, and in the peer list we try to add peers. Okay, how? We have a while, and then we say if the listener is empty, go out. But if the listener, if the pipe of the listener is empty, then break. Otherwise, the next peer file descriptor is this, and then pop. To make it easier, I created the get function, and the get function is simpler, a little bit simpler. So the get function combines front and pop. So in newer versions in the system, for example here we have the get function, I guess. Yes. In this case I make it different. I say while we get something, move. I call the content the value of each sample. So the stuff that is inside the pipe I called sample back then, and the sample has two important features, that is the space and the time, and the space I call some value, particle, and then I have the time. So a pipe entry, a sample with a certain type, in this case a JSON value, has two parts: the particle, the data itself, and then the timestamp. Because if I get some event, in some cases, it's important to know when we received the event. So this is a little bit different, but then I also used this pipe function in a signal processing context. So I made filters and regulators, and in this case I saw something special. The pipe is, I called this pipe because it's quite similar to a Linux pipe, and a pipe has some very interesting basic interesting behavior, because we can send something into the pipe and we can read something out the pipe. But for example, in the signal processing world, if we read something from a pipe, behaves similar to a file, because if we have a certain source like a file and we put the content of the file into the pipe, and we have a sender who takes the content of the file and puts it into the pipe, and then we have on the other side we have a receiver. What happens if the file content is sent completely through the pipe? Then we have to somehow signal the sender that the sender will not get information anymore. So it's similar. So a file is a pipe is similar to a file in the Linux world, and actually a pipe is similar to a transferring process. And in the transferring process, I have something similar. I have a read and a send function, send and read, and the read function as well as the send function is divided into three areas. Bigger than 0 is the number of bytes we have read. 0 is no data at the moment, but data can be expected in the future. And then below 0 means no data can be expected in the future. There is no data at the moment, and no data can be expected in the future. So this is one type of return that has a special meaning. So we have three options to do. Let's see, return types. The first one is bool, and the bool has a certain function. We can do two things. We can say true values. Values is true or false, of course. And when should we use a bool? We should use usage to indicate the success of a function. And on the other side, we have the success type, and the success type has the value is one of the base types of the whole system, of the processing system, and it's defined like this. It's an enum. Okay, it's an enum, that's interesting, but okay, good enough. And this enum is okay, this is in no. This is the success state, so this is just, these are two constants for the success function type, and the success type itself is actually in int16 type. Alias of int16 type. And the values are between something and something, so minus something and plus something, so we can say ui, what is happening? What is happening here? Greater than 0, equal to 0, and lower than 0. And this I can say positive, it's yeah, bigger than 0. Then we have pending, which is an alias for 0, and then we have an error lower than 0. Let's do it like that. Values true, positive is true of a function, and then we have an error is false. So this is the fundamental difference of usage. Indicate the success of a function, and the values can be positive, true, and error, false. And here we have the usage is usage to indicate the success of a process. So true is something, I think it's not 0, and error in false is in this case 0, but the mapping there isn't important, because the fundamental difference of these two things is that a function always, the function associates two elements, the input and the output, to each other immediately. So, and the only thing we can have is a success, positive and negative. Ooh. Yeah, positive and error here. Okay, yeah. The function does not have a pending state, but a process does have one. So it has one additional state, and this is and one type that is similar is the S size T type, and the S size T type is similar to the success type, but so it's an alias of assigned integer something, whatever, it's not important. Usage, And the usage is usage to indicate the success of a process on the one hand. And to oh yeah, grüß dich noch online. Hello, how are you doing? On the one hand, we can indicate the success of a process with the size t and return an amount of something. So that's the reason why we are using it in the transferring state, because we are transferring bytes. So we have three options: the bool, the success, and the size t. This size t is kind of special. We only need if we want to indicate the success of the process, and additionally we want to return the amount of something. So, and we have values something returned, then at the moment nothing returned, and then here we have nothing will return anymore. So that's the meaning of the S size t in the of any transferring process, for example. And the thing we will change today is that one wrong decision was made in the pipe. So the pipe is cool, but it's missing something, because E is empty and E is full. This is in bool because it's a function and the return word of a function, that's fine. But the commit and the commit and the get functions are bools. We have another option, and another option is this is maybe, I don't know, we have to check what makes the most sense, because we can split up the success function into multiple parts. We could say return types. One other option is to say we have 2 times bools, and the first bool indicates that something returned and or nothing returned, as like at the moment it's done here. Something returned true, nothing returned false. False. So, and then the second, we could make a second bool, and that is how I made one blocking of the direction. So we are able to say for any pipe we can say last sample set. Last sample set. And then we have a function returning a second bool that is telling us. The first bool is telling us, did we get something or didn't we get anything? Did we get yeah. did we get nothing? And the second bool can tell us we may get something in the future. In this case, no samples left. that's actually this is completely dumb, because I should call this samples left. Okay, we may get something in the future, true, and then we won't get anything in the future, false. So this is the second approach we could use. Nevertheless, we have return types and return types. Then we have functions. And these functions are the most important are get, commit and get. To push try is not important at the moment, but we can say last sample set is an important function, and samples left. Let's add the signature. So we have a bool commit current functions. Current functions is bool commit, bool get, last sample set void, and bool samples left. And this is the blocking mechanism for the sender. Blocking methods for sender. Okay, so samples left are if size or not last entries. So we have to invert this thing. Let's do it again. What the hell? What am I doing? What the hell? Nice. Okay, so samples left. This was before. Let's do it like that. So not this condition is the same as saying this and not this. And these two can be eliminated, so so this is the De Morgan rule. Okay. Looks fine to me. And we shouldn't use no samples left, we should use the positive thinking. No, actually. This was intended. I have to be careful. I have to be careful to my old self. This is intended. Okay. I think. I think it was intended, but it's still stupid, because it is intended because I always want to use an if as in a negative way to say if not empty game return. So I already moved this sign into the meaning of the function, but to make it simpler, to be able to say if no samples left return, come on, but the first thought is fine because I am removing this sign, which may be easier to read on the one side, on the one hand, but on the other hand, it's still not the best because it's inconsistent. Because in any if I see this sign because it means this is bad. If bad thing, this means a good thing. This is the positive meaning. So if a gamer has a game, everything is fine. But if not, then return. And this sign gets lost in this semantics. So we should do it like that. Then we have the positive thing again on the right side of the if, and it's consistent. Okay, so I will try to use this approach. So if size or no last entries, then we can get something. So now we have another problem because we have to decide which values, true. We may get something in the future. We want, no, stop, something returned. No. Something returned, yes, and nothing returned. So this is the first bool. Two bool, first bool and second bool. Alias similar to success function. Okay, so yes. So for the get function, we have a mechanism. And this mechanism says, I needed this mechanism in the context of signal processing. We read a file, a wave file or something, and we are trying to make a low pass filter or something. And then we have the filter function, and the filter process is reading from the queue, is taking elements from the samples from the queue, but at some point we have to tell the filter that the filter process is finished. The signal processing is finished. So I implemented two functions, the blocking methods for the sender. The sender can. So let's see what. Let's check what is happening in the pipe. In the pipe, we have an object. We want to move the object into the pipe. We can do this with the commit function. and not implemented at the moment, this case, and the return value could be a success function. At the moment, a success type. At the moment, it's a bool, and this bool can only tell us positive, we got something, or negative, we no element at the moment. No element at the moment. Actually, this is no element at the moment. First bool error. Nothing returned. Very important. At the moment. That's very important. That's the nothing returned at the moment. Ah, come on. Let's say positive. True. Nothing returned at the moment. We may get something in the future. Error. We won't get anything in the future. So the false case in the bool can only show us these two cases: the positive current element received, and no elements received at the moment. But we don't have the case negative, that the source is done. We have in the get function, if we have an object in the pipe, we can use the get function to retrieve the object. And this can be disabled by the sender with the function last samples set. So in this case, I've used the two bool approach for this side. The first bool is telling us first bool, for example, examples, and the get, the commit and get function, and the second bool examples would be, in this case, the samples left function. So I've implemented the receiving side already. I've implemented the case that in the signal processing context, the sender can tell us, oh, I will not send you anything anymore, and then the receiver can check this by the with the samples left function, like an end of file indicator. It's like an end of file indicator. And now we just need this for the other side. Similar. And in this case, the receiver must be able to mark the we have something else. The receiver must be able to mark the pipe as closed for input. So the sender can tell us the source is done, we won't get anything anymore. As soon as the pipe is empty and this flag is get, we don't have any samples left. On the other hand, the receiver can disable the pipe and tell us no processing will be done after the pipe is empty. So we will not be able to. It's similar. Oh, it's similar. Oh, cool. Haha. Nice. It's similar to if you are in the supermarket. If you are in the supermarket, you have multiple conveyor belts and two cashiers, for example, multiple cashiers. These are the processors, and there are multiple input queues, and the queues are the conveyor. How is this called? Conveyor belt. what the hell, I don't know, the belts for the products. So and sometimes, what is the process of shutting down one cashier system? Because if there are too many people, then they are opening in the supermarket, they are opening a new cashier system consisting of the cashier and the belt, which is the queue. So we have a processor and a queue. So the opening is easy, more or less. It's how is this process going? We have multiple people waiting on the first line. What is the first line? The line consists of two parts. Let's model this situation, because we are freaking around already, so it's fine. So supermarket opening, cashier opening process. Okay, so we have two parts of the input queue. That is an input queue database, customers outside of the inner queue as customer outside. Then we have another database, customers 1 inside the inner queue, outside of Q1, and then we have customers 1 inside Q1, which are customer 1s. Customer 1s outside customer 1s. Okay, then we have customer 1s outside are waiting behind customer 1s, and they want to be processed by a component that is cashier 1 as cache 1. Let's say as processor cache 1. Process cache 1. This is the system. Come on, add your own dedication. Yes, I know. Oh, yeah. Oh, the server is quite on the limit, so we try to use our own. We try to use our own calculation time, because we don't want to stress the system. So MISC cashier opening. Okay, so so this is open, fine. Okay, dispatching done. This is done. This is fine. Okay, Oh, pipe 2 times open, bad. Okay, so now build the cashier. What error in line file? What? I don't see it. Now I see it. Yep. Okay. So this is fine, and this is our system. This is our system. Customers outside of Q1, and then we have customers 1 inside of Q1, and then we have cashier 1. And we can say this is the component cashier system 1 as system cashier 1. So we are outside of the system or we are inside of the system. It's different. So so this is the first state. Let's keep it open. Let's keep it open. So okay, let's make oh, what the hell? What is happening? So 1 open, come on, do it, and 1 tuck. So okay, so this is our first situation. We have a cashier, and then here let's add the output. The output is of course customers processed as customer processed. And this is done with the process of course customer processed. Yeah, that's it. So we have a cashier system, customers unprocessed outside of Q1, and then we have a customers 1 inside of Q1. Inside Q1, and the cashier is processing these customers and is producing customers processed. Okay. So let's close this. And then what's the next step? Because and now if we have a process, yeah, let's make something else. Another component process of a process that is called customer arriving as CA. And this process, customer arriving, is producing customers 1 outside. So it's a producer-consumer problem. If we have a supermarket, and this supermarket, at the supermarket a lot of customers are arriving, then the queue gets filled up at first in the cashier system. Cashier 1, let's call it system cashier 1, like in the abbreviation. Yep, system cashier 1. Customers are arriving. Customers. And this process is filling up the queues. And the cashier may not be as fast as the arriving of customers. So the queues get filled up. At first, we only it's the first queue. The queues get filled up from behind. So at first this queue gets filled up, of course, and then the outside queue. So if you have nice customers, then this is a line too. maybe they are fighting already, but in a normal world, the customers line up, and then we can divide the queue into two parts. The inside, the customers who put their products already on the conveyor belt already, and then we have the customers who have their products in their baskets. So what is happening now? The cashier is checking all the time. Ooh, we can yes. We can do something else. We can model this thing quite cool, hopefully. Let's say that yep. The cashier 1 is not an asshole, but the cashier 1 is slow because the cashier 1 is sleepy already. He or she is not as fast anymore. It's late in the evening. So the cashier 1 is not as fast as the producer process, customers arriving, but cashier 1 is always checking the state of this line. He or she is looking outside of this of the space, and okay, this queue gets bigger and bigger. So we can model this as customer 1 outside will be checked by processor 1. Yes, more or less it's fine, but it's quite compact. It's quite compact, but I don't know if this is cool. Yeah, why not? Yes. Okay. But then I want to... Yes. Yeah, I think that's cool. Okay, so now cashier 1 sees that this queue is getting bigger and bigger, and then the cashier 1 is sending a signal to open a new conveyor belt, a new system. So we have a signal or an event open as event open, and processor 1 is creating this event open. And this event open event will be processed. This event, yeah, oh, So we have customer one. This is customer one, customer one, customer one. Yep, nice. And then we have customer outside. And then we have the event open, and we have cashier one, and this is cashier one, and the process is called process caching one. Caching one. I don't think this is an English word, caching. Einzug, Einkassierung, caching, yeah, it is a word. Cool. So we use this word, fine. And this cashier is already inside the system. We have two types of people in the system. We have the customers and we have the cashier. And the cashier is cashier one connects to the process. So the process, the caching process has two inputs, has three inputs. The first input is we need a person a person as a resource to fulfill the requirements of the process, and then we need customers that we can process. And this cashier is in the state of allocated. And then we have an open event. This caching process with the cashier can produce an open event. Okay, so and this open event, is using a component called the allocating as process allocate, and EO is using this. Okay, we are allocating. What are we allocating? We are allocating a free cashier one allocated. And then we have another cashier 2. Outside of the system as database cashier 2 in the state unallocated as cashier 1 unallocated, and the process of allocating needs this resource, and with this is able to create a new system, not create a new system, but moving the cashier to a different state. That is, we have cashier 2 allocated, cashier 2, and the allocating process PA is moving the unallocated cashier cashier 2 unallocated and moves it to you holy moly, what the hell is going on? Yep. Cashier 2 allocated. Now I have I've done something strange. Yes, system 2. We have a new system, cashier system 2. Yes, nice. We should call it cashier system 2. So, and here now we have another process that is called the caching process 2. And cashier 2 is entering or is used by the caching process 2. Okay, and then finally now it gets interesting because we will have an error at this point. So caching, yes, and now we are on a certain point, because I always try to make this to a planar graph, and I think now it's hard for plan to ML. Okay, let's see. Okay, so we have the customers inside of customers 2 inside of Q2, customers 2, and these customers will be connected to caching process 2. Nice. And then, because the system was there before, but with the event open, the allocating process, that's in process. That's not done immediately, because the event is done at some point. The event is created not immediately. It's created sometime during the caching 1 process. So customers are arriving, the cashier tries to process the customers, but it's getting more and more, and it's always checking. It's some customers are waiting already, but I could still manage the workload maybe, and then it's getting bigger and bigger, and then okay, now I have to send the event. Then the cashier 1 decides to create the open event. This takes some time, so the queue gets bigger, and then we have an cashier 2 unallocated doing something else, hopefully. But this cashier 2 has to exit. The cashier 2 has a certain state. The cashier 2 is used by another process that is, for example, ordering products in the shelf or something, and then the cashier 2 has to get unallocated first, and then we have a unallocated cashier. So even this resource, we need this resource and this resource to produce this resource and or state. So this takes some time already. Okay, so but after some time we have created this event, and we have found a cashier 2 who is willing to enter this system of caching 2 for cashier 2. System cache, let's call this system caching 2, 1 and 2. Okay, so and let's give it yeah. Okay, so Of course, now what is the reason for all of this? Because we want to flush out or to minimize this thing. So we have another source and not another. We have created another sink, and so the customers outside can now connect to the inner queue of customer 2. No, that's cashier 2, but customer 2, I think. Yes. So now we have activated the second system, and now we have a 2. We have 2 currents of customers. Okay. We could theoretically say in the allocating process, cashier 1 is sending an acknowledge event to the caching 1. Maybe we could. Should we try to do it? Event acknowledge EA. Let's see if this doesn't. Hopefully this makes sense. So we have from process caching 1 to and EA from process allocating. Yeah. Yeah. I understand, but we should yeah, that's too much that's too much. So we will remove this, but theoretically we could create a second error back to the cashier system. So this is an information current, and the current of course is always a loop. But in this case we can always make an abstraction of the current. The important thing is to know that every current is a loop, and in this case the loop would be to create an open event, and this process is creating an acknowledge. Okay, so of course the caching 2 process is now connected with this thing, and hopefully this is working. Cashier 2 unallocated. Yes, let's try this. What is happening now? Yeah, that's what I thought. It's already in a very overloaded state, but let's try the final connection. The final connection is the process of caching 2 is also creating customers processed, like process caching 1. It's the same. So yep, damn it. Yeah, that's what I thought. That's what I thought. I don't think that it's still in planar graph because we could draw this line from here to here. Then it's still a planar graph, but I don't know if we are able to make this more beautiful, but we try. Okay, so what could we do? Yes, we could. Yes, we could say, whoa. Let's move this for a moment here. On top. Oh no, you are not on top anymore. So let's move you up here. Okay, let's make this more beautiful. Ooh, hard but possible. Okay. I want to say the event of process 1 is like this, and the customer's process is done like this, and the customer's processed. Okay, let's see what is happening now. Oh, no, but oh, okay. So event, the cashier 1 allocated, cashier 1 should and cashier 2 is PC2 cashier 2. Yeah. Oh. So, whoa, actually, this looks quite cool. Yes, actually, I'm satisfied. Final thing we will add is a damn it. I want to. That's so hard. I want to switch these two, this part and this part. Maybe we are able to switch these two parts. I want this thing to be below. Okay, let's add the database customers unprocessed as CU. And that's the purpose of the whole system. And the customers unprocessed are arriving. What is CA? Customers arriving. That's wrong because that's a process. PA, do we have a PA? Process allocating. CA, okay, that's P alloc. CA we will change to P arrive. And this P arrive, the customers, the customers unprocessed enter the state. Okay. And now we want to switch to these two because then we can make a big system statement of supermarketing. Okay. Arriving and shopping. So the customers are arriving and shopping. This also is a multiple stage process, but at this point we make, at this part we make the thing abstract. Okay. Now we try to switch these two parts. Hopefully this is working. Okay. And we could try to event open is yeah, this wasn't working. How can I I would like to move these two parts in between here, and then this part on the left, but this wasn't working. This wasn't working because I tried to yes, let's try to save the important parts. One part is caching, process caching 1 to event open. Okay, still working. Okay, fine. This is the first part. Then customers processed. And this part, yep. And then I have event open to alloc, everything with alloc. And then I have cashier 2. This is the part we want to change. Okay. Unstable. Okay, I want to save this working state. Okay. One moment. Very important. Oh. supermarket. Okay, so now I can try to improve this. Okay. Oh, what the hell? So, So today we get the feeling of systems. Okay, so I want this event to be directly on the right. Then event open should be connected right to allocating. Allocating should be to the cashier, right? Okay, that's fine. This I will deactivate this for a moment, but the cashier 2 should be connected directly to process 2. And the processed customers should be connected down to here and down to here. Why? Okay. This is strange. Why is this happening? Component foo sf. So maybe we can arrange the stuff in a different way. Okay, let's check. This is one part. This is another part. So then we have the customers outside. And the customers outside, yes, this is customer 1, customer outside. Okay, customer 1 outside. Then customer 1, yeah, customer, Then customers outside are connected to customers 2. Yeah. This is one part. This is another part. And then we have cashier 1. Yeah, maybe it makes sense to say cashier 1 is directly connected to PC 1. Okay. No. I want these two in between. Maybe there is not enough space. Wie kann ich das Spacing in Blend UML Graphen erhöhen. Ja, horizontal spacing. Stop. Okay, let's check. Skin param. Okay, this didn't do the job. Trenne. Yeah, spacing and margin. Yes, we can use hidden stuff. Yes, maybe this makes sense, because we could say we could say that a hidden connection between. We have a hidden connection between the customers outside, hidden to allocating, process allocating. P alloc. The cashier allocated. Oh, we have a storm. Hopefully the stream and hopefully the system is not crashing. Oh my god. So now everything is completely strange. This looks completely ugly. Okay, let's make it a little bit simpler again. Oh yes, better. Oh yes. Then this is hidden. Cashier allocated. Yes, even better. Oh. Almost. We have. Yeah. So now we make. So the skin param wasn't working. Oh, come on, I'm not. So. Okay, this isn't changing anything. Okay, but now we want to have a supermarket, and this supermarket is, we have database, customers, processed and unprocessed, and all the other stuff is in the component supermarketing as process supermarket. And this process contains the customers arriving, customers outside, event open, allocating all the stuff. Yes, more or less. Let's try a completely different approach. Swap all the stuff. Swap all the stuff. Because then we may have more space. Horizontally, because of the text, it's getting too much pressure, like it's like some kind of pressure. So we have customers unprocessed go to the arrive go to customers waiting outside. Then the system one, oh come on, I have to switch all the stuff. Customers one go into your yes, cashier unallocated. Better. Now, this is okay, this is okay. I was too greedy. this is the situation in which we were too greedy. I was too greedy. So, but maybe we can fix it. I have customer outside the queue, and then I have customers one. Yes. And customers one is okay, like this. Cashier one. Process one gets cashier one. Yes. No, from top. From top. Process caching one from top. Yes. Cache allocated caching. Now customers one inside queue must be left. Somehow they aren't. Oh, is it better to? Yes, we could. Okay. Every error, every connection that is not crossing the border should be in the system itself. Should be defined inside the system itself. So we have a process one with cashier with customer one. Yes. And we have a cashier one. So two connections should be inside this system. Okay. Then we have then we have these connections, these two connections in this system. Okay, customers. let's say process 1, customer 1. And then we have down. And then in the opposite. Oh, come on. I was too greedy. Cashier 1. Customer 2 is no, here. Yes, and then you have cashier 2, and cashier 2 must be, this must be switched. PC2 like this. Does this make sense? Let's just flip and move around the stuff for a moment. Okay, it's getting a little better. Yes, but I want to switch these two. I want to switch these two. I want to say customer 1 is connected to PC1. Yes, I just want to switch this with this. Better. A little bit better. Yes. Yeah. Customers 2, this is on the left side. This is on the left side. Welcome on. Yeah. It could be a planar graph, but it's not doing what I want. We are very close. I want to fix this. Come on, this should be possible. This should be possible. What kind of orientation do we want? Do we want to have left or right? From customers unprocessed should be left. Okay, customers unprocessed should be from left to right. Arrive should be from left to right. Customers waiting outside. This thing is this error, and yes, this is strange because I want to have customers waiting outside to customer 1. Like this. Yes. Okay. Yes, that's one strange thing. Yeah. Okay, I think I have to give up. Okay. because that's too fancy. We had the planner graph already, so let's keep the old version. It would be cool to define the customers unprocessed and processed outside, but okay, whatever. Git stash cashier pu git stash p all load build. So this was the best version we had, and we should keep it that way, because here we can see everything we need. We have the customers unprocessed, they are arriving and shopping, and then they are finished with arriving and shopping. Then they are waiting outside of the caching systems. Some customers, there are no customers are moving to this pipe because there is no cashier in the seat. So they are going to belt 1. The caching process is using the cashier. The caching process is using the resource cashier and the customers to produce the customers processed, and eventually at some time after checking this, the size of this queue is the caching process is creating an open event, and the allocating process is checking is finding a cashier and is allocating the cashier too. Then we have a second, we have produced a second path for the customer current. So now customers are moving, who are waiting are moving to the belt 2, and the caching 2 process can join the caching processing. Okay, so that's quite cool. So but now so that was the opening. That was the opening. Yes, let's also say this is opening and closing, because what is happening, what is happening now? The cashier 1 is checking in the caching process the size of the queue of customers who are waiting outside of the caching systems. And if this queue is moving under a certain threshold, then we are deactivating again, we are freeing this resource, because this resource gets allocated and we use this resource to fulfill our process, but because this is a kind of load balancing, but we want to free this resource again. So how can this be done? The caching 1 process is creating a close event, and then we have a deallocating event, which is removing this cashier again, and then the flow of cashiers is in the opposite. And then this process is not, and that's the important part. Then this process can only work. I have found an error, I think. I have found an error. that is, oh, come on. Yes, mm-hmm. Mm-hmm, mm-hmm, mm-hmm. Yeah, that's something I have to define still. Um, if these arrows are solid lines, if these lines are solid, in general, I interpret these lines as a requirement, all the requirement to move outside in one or multiple directions. And again, if I have, yeah, that's not working. My definition is not working, so I have to define something else. I tried to define a solid line as a requirement, as a hard requirement. To fire a transition, I want, yeah. I want to this thing to be similar, like I want to merge the functions of a Petri net graph, of a Petri net. And in a Petri net, to fire a transition, we need all inputs. And I wanted to define a solid line as a requirement to fire the transition or the process. So if a process has two solid lines or multiple solid lines as input, then all resources are required. And in this case, I could make these lines dashed, because sometimes I get an event from here, then I get an event from here, and sometimes I get an event from here. And here we have a requirement that both like this, both inputs must be fulfilled. This could be dashed, this could be a dashed error, but on the other side, I want the same for outgoing errors. So one process can produce multiple stuff, and in this case it would be customers processed and an event. And here we have also multiple events. And my approach was to define the outgoing errors as, if solid, then they are created at the same time. And if dashed, they are created independently, like this, like here. But yeah, that's not working. It would be working in this case because I made an almost this is a bipartite graph. That means we have two types of symbols that are not connected to the same type. So this, we have square ones, and no square is connected to another square, and no database symbol, no component is connected to each other, and no database is connected to each other. As you can see, this means we have two groups of, this is a special type of graph, and in such type, in such class of graphs, we are able to define the input, the arrows are divided into two sections. and then we can define this as an input vector, this is as an output line, this is an output line, this is an input line. But do we have an example here? We are also able to, yes, to abstract the data sent between. We are able to remove the data between two processes in the case we don't care about what is sent in like overview systems. So in this case we cannot distinguish between input and output line. So I have to come up with something different. Maybe I could define two types of abstraction diagrams. In such abstraction we could do this. This is something I'm I'm still wondering what I should do, but okay, whatever. So we don't care at the moment, but unfortunately these errors have a different meaning and we don't see this meaning immediately. That's bad, because here we have the meaning that the process can have input from multiple sides and at different time points, and here we need all the stuff for the process. That's bad. It's unfortunate. But okay, so back to the explanation. What is happening during the closing process? The cashier 1 detects the shrinking queue outside of the caching system, and that's the reason why we have to extend our pipe. This is the reason why we have to extend our pipe. The cashier 1 is detecting the shrinking queue, this queue. Then the cashier sends an event close. Okay, then we have a deallocating process. These two errors are reverted. And this cashier is moving out, but not immediately, because what let's say cashier 2 is going away immediately, then this queue isn't empty. So if the cashier 1 says, yeah, okay, you are free to go, then the cashier 2 should still be bound to the caching 2 process, because the customers 2 already put their products onto the belt. So we have to somehow, and this signal can be seen in real life, because this cashier then is sending a signal to the customers outside. Actually the open event is done by cashier 1, because the cashier 1 detects the overload, and usually cashier 2 is then observing the same thing, and we could theoretically the same error, we have the same error in this side, at this side. Let's see if this is still doable. Customers outside, customers outside, customers outside want to PC2. Is this possible? Wow, it's too overloaded. It's just too overloaded. Okay, but we would have the same error on this side, and then the cashier 2 is closing this queue, this system. So it's sending an event, a signal to the customers, and they can recognize that this movement from outside to this belt shouldn't be done, and then the transfer into this queue is stopped, and then the cashier 2 is emptying this queue and then can be released. And that's exactly what we want to implement. This was quite a journey to explain, because yeah, I used too much time. I tried to put everything in this diagram, but okay. So can we emphasize this input and this output? Theoretically, we could say, but it's cool because we will learn a lot of Plan2ML. If I do this, then we have a different shape. Yeah, wow, why not? I think this is better. Okay, so now I think maybe it's better to see that this is an input and this is an output. At least we have some distinction. And then the last thing I want to do is to input this on the side. So the P arrive is okay, let's keep it. Let's keep it that way. So I think this is fine. So we need, for this process to work, we need a function to tell the rest of the system, the producer system, which is giving us the samples into our queue. We need a signaling mechanism to be able to stop the input stream. This is it. This is what we want to do in the next 15 minutes. Okay, dog update. Okay. Now, the question is, so for our queue, we want to be able to disable the commit function, which can be disabled, should be disabled by the receiver, to tell the rest of the system the sync is finished. It's not doing anything anymore. In Linux pipes, if we have Linux pipes, and if the sync is finished, then we have to be careful, because if we make a commit in the Linux world, it's called write, because it's a file and we are writing in the file. And if we write into the file, although the sync is disconnected, then we get an SIG pipe signal, SIG pipe. We can deactivate this, I think. No, for pipes we can't disable this behavior. We can only disable this behavior for sockets, I think. Yeah, I'm not sure, but I think there is an option, no signal for sockets. If we create the socket, then we can say, please don't give us, if we write into a socket with a missing end or a closed end, then please don't give us a signal, but tell us that the write function failed. For pipes, we have to register. We have we have not register. We have to keep the one end open. That's possible. Okay, so the receiver end, we can duplicate the file descriptor of the receiving end. This is what we have done in the file executing process. File executing process. Do we have this thing somewhere? File executing. We did this here. The parent pipe states are after fork in the parent process, and the pipe states after fork in the child process. And here we can see that we are reading the pipe std out and stdr, and we have std in, and as you can see, for this pipe, for the std out pipe, we closed the read file descriptor. We have cloned all file descriptors at first, and then each process is closing the part it doesn't need. For example, the child process does not want to read the std out part of the pipe, so it's closing this file descriptor. And the parent doesn't want to write into std out, because for the parent std out is out, not in. So we don't want to write into this pipe. So they are closing each part they don't use. But in the case of std in, if this process has finished and closed the read end of the pipe, and we try to write into the pipe, then we get a SIG pipe, a signal in Linux which tells us, okay, you try to write into a pipe that isn't receiving anything anymore. So if we write, as soon as this process has finished and we do a write into the pipe, then this process, the parent process, is getting a SIG pipe signal from Linux, from the operating system, and then this process gets shut down as well. And this isn't what we want, so we keep this read file descriptor open. So if this file descriptor is closed, then we still have a file descriptor, and then we can check with a different approach, with a different mechanism, if the child process is still here. Bah. It's hard for me to explain such complex things in English. Boah. But it's a very good practice. Okay, so we want to implement a similar behavior. We have the same things. We have processes and we have pipes, but not on the operating system level, but inside of the application we have processes, and the processes have to communicate to each other. And we call this thing, one approach is we have multiple, we can do whatever we want, because the processes do not define the interfaces or the data that is transferred. So this is open to the programmer. But one way is to use this thing which I called pipe, and I want to have a good tool for the beginning, for standard, for common situations. I want a good tool to use that should be thread safe. So it should one important thing for me is to make this thing thread safe. Maybe we can disable the thread safety to tell the thing that we don't want to log a mutex. I don't know, but at first it will just log a mutex and that's it. So so now the first decision is to do use check move semantics. No, yes, use success decision. We have to make a decision. Use success or to bool types. This is the first question we have to answer. Then maybe we have to rename functions if we decide to use the success system. I think we should switch if we switch using, in the case of using the success type, then we have to do remove functions is last sample set. Not remove functions function sample left. Rename function last sample set. To maybe source done. Source done set. Yeah. Rename function last sample set samples left. Maybe we could say, yeah, no, remove function, because, and then change signature of function get. if we choose to do so. Otherwise, I think it's better to make a breaking change. Of course. Use and check moves and okay, this is something else. Because I want to have add receiver functions, which are add function sync done set and change signature of function commit bool get to success get. Bool commit to success commit. So now it's interesting because okay. I think, oh yes, okay, I understand. I remember why I wanted to use the bool approach. Because I wanted to try I didn't want to have a dependency to the processing header. Yes, but I have because of this config stuff and this thing. Ah, yes. Remove mutex includes pipe. Do not include mutex if no drivers. Fix mutex. I think it's in this area. Git blame pipe. Poor hoho. What? One commit? Which one? Ah. Yes, this is no. What? Confused. I am confused. Okay, whatever. Whatever. So yes, so we have a dependency, a pipe, yeah. I'm not quite happy with this dependency. But on the other side, it's... Is this okay? Okay, let's keep it that way. Oh, yeah. Pop get Okay, one thing I want to do is the front. The front thing should. This is. Entry mutex if not size. I want to have some. What should I return? I return. So okay. Return. What a new type of this? Is this possible? No samples left that depend on parameter. Nothing left. No samples left. Nothing left. Is not samples left. Not samples left. Whoa. Whoa, this was. Okay, so samples left. Guard lock. Interesting. And remember log to push try. So this is the next thing. Oh, come on. The next thing is that these pipes can be connected to each other, so we can have an hierarchy of pipes. And if this is the reason why I call this commit. If we move an object into the pipe with commit and other pipes are connected as children to the pipe, then there is another function that is called to push try. And we are able to duplicate samples. And this signal nothing left, is propagated through the chain. If I have nothing left, if I don't have any samples left, if my samples left tells me that I don't have anything in the chain left and the flag is set, I propagate this flag in the function to push try. This means samples left. Okay. So theoretically I could make a block here and say nothing left is no size and Mm-hmm, mm-hmm, mm-hmm. If not size and last entries, we have decremented size, and if we don't have any size and last entries, yeah, phew. At the moment I don't care about performance, I just want to make it stable. So we have removed this function, something pushed. We have removed this function, samples left. Yeah. Rename function, last samples set to source done set. Source done. What this is so the compile process is so giving it all. Okay. So last time rename function, yeah, to source done set. Okay, yeah, I think somehow I have decided to switch to the success approach, but now we have to be careful, because now I have to change everything in the system, and I will do this by changing this function to front old. Then we have entries is entries. That's okay, that's the queue itself. So this is our own function. So if this function is used somehow, oh yes, it is used in the TCP listening and in the system debugging area. I want to remove this function. No, I don't want to remove this function. No, I don't want to remove this function. It's still an important function. Front. Mm-hmm. This thing, this function is giving me something special. The function front is defined as the function front gives me an element of type t. We don't have the return value bool or something, so we don't have to change it. And the function front and pop are used in certain circumstances. The function front is used if I don't want to pop this thing. Okay, so I have to change the pop. Maybe. Yep. I will add this function first. Data blocking set, m data blocking. What is this thing doing? If would block and data blocking, I will break. Yes, this entry will be transferred. Remove it. If entry is empty, break, then this can't happen. Okay. If my entries are empty, break. Child list size. Okay. Get, pop. These three functions. Pop. How can I pop? I think let's try to say positive. If we define this function as success, then we can have positive. We can say if not size, then pending. And if sync done, then we can return -1. Source done, sync done, false. Then we say avoid sync done set, sync done true. I try to pop if sync done this is a flag that does not need to be mutex. The reason why I'm mutexing here is because I'm using this size. Sync done. Pop. The same for the get. If sync done, return -1. If the sync is done, we cannot get anything. If we don't have a size, then it's pending. If the sync isn't done, then we can't return negative. Then we have to try at least. If we don't have anything at the moment, then we say we are pending. Otherwise we say we are positive. But now we have changed 2 functions, 3 functions. Oh yes. No, this was false. This is source done. This is source done. And here we have if sync done. Return -1. Yes, that's it. Okay, success. If size bigger than size max, then we can at the moment not insert something, and otherwise we make a positive return. Yes, okay. And these are the functions that actually change if we decide to change the interface, and I think it's okay. Is empty, is full. Yes, why not saying bool source done. I think I will change to this sooner or later, but whatever. What the hell is happening? Okay. So we have a source done, and if source done, then we can't pop anymore. We can't get anymore. If we can't get something out of our and then we have to propagate that the source. Yes. No, stop. If nothing left. Oh, this is important. If not size and source done, then return -1. This is it. Okay. And again, if. So this is different. This is different. Because And yeah, this is interesting because it's behaving in a different way. If I set the flag that nothing else will arrive, that we don't get any samples anymore, then the queue can still be full. So the get, if the source is done, I can still get something because but the commit must be closed immediately as soon as the sync done flag is set. Yeah. Okay. Independent of the size, here I have to check the size and it must be inside of the mutex. In this case, I can, independent of the content of the and the state of the pipe and the queue, I can say stop it, like in the supermarket example. Sync done. I can set sync done. Okay. So what again? What is the M data blocking doing? Would block. What does this mean? All children ready for this next entry? If would block true and data blocking, and data blocking is default true, I can set data blocking Okay. I can set this to false, then this entry will be transferred. Remove it. We remove the entry. We have ooh. Okay, okay. Fine to me. Fine to me. Okay, let's check the to-dos. Oh, come on. To do change signature of functions. Bool commit to bool pop to success pop. Oh, come on. Bool get. Oh, come on. Receive functions. This is yep. Remove functions using success. Change sender functions. Samples left, samples. Bool pop to success pop. Now, now we change the name of these functions and see what we have destroyed. So this is pop new. This is get new. And this is commit new. What? Huh? Bool okay, yeah. Sync done. Yep. So this is it. Has no member commit. Okay, I have to change my own commit too. Oh, iter of my child list commit new. Yeah, let's. Okay, now we have different. Yeah, we have how many. What? It's actually this is not as bad as I thought. Lobby interacting class does not have a member get. Okay, lobby interacting. Actually, it's more important to check the processing code. Paging, lobbying, paging, account, paging, account, main, paging, main, account, main. Okay, yes or no, it's staged. Okay, damn it. Okay, so then no, go to main first, main, then game selecting, get. Oh, okay. Now we have to change this signature to say if not positive, and at the same time I'm checking the connection itself. Get, if not get, I'm doing nothing. Yeah, okay. Okay. Get new. Yes, I have to. Yeah, I don't care. It's okay for me at the moment. So, get. If not positive. Looks kind of ugly. This looks kind of ugly. This looks kind of ugly. I have two versions. I can do this with the new approach. I can do this, or I can do this. Success is equal to And before that I had, let's try to rename this to have the real one. If I don't get a key, I break. Yes, I think in this special case, I think it's better to use the first and second bool approach, because the code is cleaner in this case, and for this scenario it was fine, because we can make two checks. We can check, we have a producer and the lifetime of the producer and the lifetime, the lifetime of the processors and the lifetime of the stream can be different. I think. So that's cool, because then, yeah, this is one to do. Front returns new value. Yes, if empty, if Q is empty. So okay, this is fine to me. I don't want this thing to crash. Actually, this is a bad case. It's a bad case, and it's behaving in a bad. If we do this, then it's definitely then we have fucked up somehow. So okay, we shouldn't do that. But yes, I think the flex can still be used. That's okay. So these files, so this is the second bool already. Yeah, that's okay. So source done. And the pop cannot return a success, but only a bool. Maybe we can make an overloaded version. Maybe we can make an overloaded version. Is this possible? Let's try. Let's make a pop returning a bool, and then we say if not size, we didn't get anything, otherwise we got something. Then we have a second pop returning a success. I don't know if this is possible. If it's not possible, then we remove the stuff. Okay, so and then the success types. So bool get return false, return true. And then we have a get bool version and then a get. Okay, game selecting drop back to old school version and then commit bool version does not check this. Commit and then return true at this point and then commit. Let's see what's happening. Cannot be overlaid with bool pipe for what? Success error cannot be overloaded with yeah, makes sense. This makes sense because it can cast the stuff. Okay. So then we have chosen the other thing, the other version, because we still have the possibility to check. Come on. Yeah. Okay. Okay, I don't have a commit new. Commit. Yeah. Yes. Okay, so wait a moment. Sync done set. Yes, that's cool, but actually oh, damn it. I do want this function. No samples left. And I should call this entry, not sample. Sample. Yeah, no entries left. Okay, I will. Data blocking set, okay, is full. Okay, so bool entries left const source done, yeah. Nothing left is not entries left. And this is the content. Return entries left is size or this. Or not source done, entries left. git diff pipe. Let's check this. Okay, samples, last sample set. Okay, last entries is no samples left. Const. Okay. Swapped. Okay. No samples left changed to entries left. In function front, if not size, return a new element. Okay, bad, but not very strange bad. Still strange bad. So we are not allowed to do this. Actually, this is kind of an exception. Should we throw an exception? No. Let's keep it that way at the moment. So no samples left is the same as not entries left. Okay. Source done set. Last sample set source done. Okay. So I think this is it actually. Okay, I think. Should we? Yes. Oh, what the hell? What is going on? Why? This was. Yeah, I know. Now I understand why this isn't const. Boah. Yes, let's check if we can connect. Telnet localhost 4000. Yeah. Can we create something? Okay. I think this should be okay. Telnet localhost 3000. Okay. 2. Oi. Yes, because it's the log. Yeah. Okay. Oh, nice. Help. Oh. Detailed. The command system is so cool. Okay. Yes, I think everything is still working. Okay. I don't know if one of these are using what is the interface change at the moment? The interface change is that we have removed last sample set. Okay, and no samples left has been renamed to no entries left. Yeah, perfect. The reason is why I wanted to change the interface is because the interface was only used in an internal program, an internal signal processing program, and that's the only place. So it's still okay, I think. And okay, so let's check again. This is in the public interface. This means in the public interface of the base class. This means that the sender can set source done set. The sender or the source can execute this function source done set. And the receiver can check two things. The first one is if the source is done, but this is not as important as if there are entries left. On the other side, the receiver can execute function sync done set, and if the sync is done, these two functions are one of the side for each side, used for each side. This is used by the sender. Let's make it used by sender, and this is used by receiver. And optional sync done is sync done set. No. Source done. Let's make this used by receiver, sync done set and entries left, and source done set is used by sender. The sender sets a flag and checks this flag, and the receiver sets this flag and checks a more complicated situation. The receiver wants to end its job. System. Yep. The receiver wants to end its job only if the flag is set and the queue is empty. And the sender wants to stop as soon as the input of the queue is blocked. Okay. So, I think this is it. And I think we can change interface. Okay, I think this is it for today. Let's try to run the tests. GitHub. We have a build test. Hopefully this is working. Ay. Let's Oh no, stop. I don't want to make it like this. I want to do it, I don't want to do it like this. Run workflow, run workflow. I'm not an expert in workflows, but come on, and cross arm. Yeah, let's make it, it's the same, but whatever. So all workflows. Okay. Oh, we have to update the to-dos because we are finished. Use success bool to bool types. Use to bool types. Okay, decision is made. Using success. We are not using success, but we are using to bool types means using. Come on. We had to come on. Rename last samples set. Rename function last sample set to source done set. Okay, and then we changed the function rename function no samples left to entries left. So this is done, and then add functions and add functions. Oh, come on, I'm so tired. Oh, come on. So it's done. Yep. Sync done. And sync done set. I think this is it. Entries left, source done set, source done, sync done set, sync done. Okay. Okay, use and check move semantics. Oh, okay. Oh, we are still not finished. But okay, this will be done in another stream because I want to use the move semantics and oh, what is happening here? Oh, I didn't expect this to happen. What could not? What? What the hell? Ah. Bah. Ich bekomme bei den GitHub Actions diesen Fehler. Schauen wir mal. Wenn der Reactions die erforderliche Version bla 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 nicht bekommt, ja, was möchtest du denn? This is the reason why such things are. It's just one thing. We have to maintain. Okay. Was will der denn? Ah, ja, kann man. Stell dir das Ich habe es relativ minimal gehalten, aber Build test. Oh. It's not even using the new version. I'm so stupid. Oh. What the hell? Tools rename, relog member variable, remove that code, but didn't test it. Nice. So, okay. Okay, and what should we do here? Come on. What? No, here, GitHub workflows, so Windows native and and CI. Windows native toolset. Uses, blah blah blah, set up stuff. Or GitHub, blah blah blah, to reproduce, blah blah blah, was not found. Think it is a breaking change did of the versioning, nice. Fixed in. Let's try to switch to 4. I don't know. Hopefully this is the solution. Okay. And try a Microsoft fix. So, how can I remove all the stuff? Oi. Yeah, completely new. I want to remove all the workflows, but I don't know how. Whatever. So, nothing special will be happening now. You can go to sleep because I'm just cleaning up the stuff. Next time we try to check the move semantics of the pipe. And this will be another special. This is this part. Pipe core check move semantics. Yeah, okay. I think it's okay. The move semantics means that if we have an object pointing to some data, and the object has implemented the move in constructor, then we want to just move the object into the pipe, but not the data. And yes, we have to check the signature. folder. This is working. All workflows. Oh, okay, cool. So I'm restarting all the stuff. Run and run and run and run. Okay. Yes, and it seems that yeah, so commit. The commit is interesting. I don't know what is the best way to do this, because maybe we should what kind of signature should we use here? Is it okay to use by value here, because then we may have a complete copy of the particle, or we may it's even okay, what the hell? Wie funktioniert Attributes Q Emplace Back? Gibt es das überhaupt? Oh, Windows Native here, come on. Oh, okay. Yeah, we have to we have to fix stuff now. Okay, why? What is happening on the Windows? To push up being compiled. Klar, syntax error, missing home before entries left. In TCP what? Compiling failed TCP. Listening error not. Yes. Okay. Pipe. Not. Then hopefully this is working. I think so. Hopefully. Okay. Nice. Pipe. Remove not for my Microsoft compiler. Okay. Windows native. Oh, yep. Run workflow. I think this was okay. So if Windows is running again, I hope. Yes, I hope this was fine. Yep. Update processing core. Okay. Then GitHub. Git merge. Okay. So core pipe. And I think in place back. What is better? Gib mir keine Methode im Blende für Q. Die Methode im Blende ist mehr von Vektor. Dicke und anderen Container, die das sind im Blende durch Konstruktion an Ort und Stelle möglich. Die Verwendung neues Warteschlange. Hier ist zum Beispiel Q in place. Ja, pfui. Okay, commit. Okay, let's try to. I can't stop, but I have to stop. And place. STD move particle. Oh. I don't know if this is okay. Oh, new initializer treated as compound bubble. Yeah, not that easy. Oh, and in initial instantiation of what the required from. Always the same. Okay. I have no clue. Oh, come on. CMake error. What? Why? Visual Studio installer. What is happening? Okay, what? Start application Mason. Process creating on and done. Start application CMake. That's strange. Build application CMake is fine. What? Okay, this is interesting, but I don't care at the moment. Okay, whatever. Oh, yeah. Okay. So, in place. Let's try the first. Let's try the first step. Okay. I can't emplace back. Why? Entries. Entries is a queue of pipe entry of a certain type. Okay. If 0, else, and if. This is the first. This is the first version. Okay, and this is the second one. Actually, this. I want to emplace. Aha, what? Okay, Erklärung. Fügt ein neues Element. That's cool. I can't decide which one is better. Die für ein Element, die man wandert, ohne zu erstellen, was die Effizienz verbessern kann. Hier ist ein. I have a struct x and epsilon. I have a constructor. A B. So maybe I need a special constructor for this, which may be possible. Boah, that's hardcore. That's hardcore. I think this is part of another stream, but I want to at least try something. This is an entry, a struct pipe entry, and this pipe entry needs a constructor of T P particle time pt1 and particle time pt2 should be copy constructor of something. Boah, that's okay, that's I have to be a little bit fresher for this. Mhm. No matching function to call. Message. No matching function to call. Oh, yes. Mhm. Do I need this now? This is cool. Wenn ich anstatt des Double Y Eintrags einen Vektor verwenden würde, müsste ich im Maastricht-Konstruktor dann ein müsste sollte ich in meinem Konstruktor dann einen Move Aufruf in der Initializer-Liste machen. Keinen Plan. Weil das wäre dann der Copy-Konstruktor eigentlich. Ja, wenn du das Medium. Schauen wir mal. Na, okay. Oh, ja, zweimal, so wie ich es gemacht habe. Jetzt lesen wir uns das mal durch. Ja, wenn du einen Weg verwendest und einen solchen Weg in den Konstruktor übergibst, solltest du den Move verwenden, um die Effizienz zu maximieren. Dies verhindert eine unangenehme Effekte, indem du bist. Da muss man aufpassen, wenn man was nicht versteht und sich von ChatGPT was erklären lässt. Und Meister verwendet int und einen Vektor int an. B. B wird gemoved in move. Is this real? I don't know. So this would be the diff. And if I commit something, then I can decide from the outside if I move this into the function commit. So this is actually by value, and I could move this value into the function, and then I move the particle. Definition, Meister. Let's check this explanation. Mhm. Mhm. Jemand merkte ihn erstellen und mit in dem Emplace Aufruf verschoben. Und dort wird der Weg der Verschwörung schon kopiert, was in begrüßen McDonald's übliche findet. Ist das gleich effizient, wenn ich einen der Move Aufrufe entferne? Nein, das ist eine Konstruktion. What the hell? Und das ohne what stop bitte stop. Sind da beide Fälle abgedeckt? Entfernt der Move auf das Entscheidung aktiviert. Beispiel Move in ohne Move in Konstrukt. Und im Main Move Analyse effizient mit Move der Wiener Plätze verschoben. Und der Move war im what? Und dann ohne Move wird eine Kopie erstellen, so wie mit Move in Konstruktor. Blablabla, ohne Move. Und wenn ich den Move Aufruf im Emplace entferne, ist das gleich F. Oh, ohne Move, interessant. Also das gleiche. Ja, okay, macht ja mehr oder weniger Sinn. Also, mein Problem ist, dass ich weiß grundsätzlich, was ein Move ist, aber das Emplace ist an dieser Stelle eigentlich mein Ding. Was ist denn ein Emplace? Auch schon wieder ein Copy. Das müsste dann zweistufig sein. Okay. Ja. Yes, we should check this. We should check this the next time. We will create a class that implements a move construct, and then we will test this stuff. And that's it. Okay. So this is it for today, and thanks for watching. If someone is still watching this. Okay. CMake app access run command prompt type native framework. What happened here? Error process completed with exit code 1. Okay, good night. See you next time.